Okay, hi guys. Today I'll just be covering a summary of the organic chemistry reactions and whatever that we learn in the syllabus. So I'll try my best to cover as much as I know and as much as I can. Again, I'm not a perfectionist. I'm not a master, really a master at it. I just, yeah. Maybe this summaries will be helpful to you, so it'd be good. Okay, so let's consolidate all of the organic chemistry reactions in this video, and I'll try my best to explain whatever concepts that arise with it. Okay, so firstly, we have our most um, basic organic compound. It's an alkane, right? So, yep, here's the compound here, alkane. So, if we know about the molecular, the general formula, okay, how we deduce it, we can just use propane for example. So, there are 3 carbons and there are 8 hydrogen atoms. So, then we can break it down to see this. So then we get CnH2n plus 2. So this is our alkane general formula. So the first reaction we learn about the reaction of alkane is that the mole substitution of a hydrogen atom for a halogen atom. So the reagent condition we use here is limited X2, where X is chlorine, bromine, right, iodine. Okay, so and then we use UV light. So why the limited halogen uh, that we use here is because we want to do a mono substitution. If we put excess or like a lot, not limited, right? Then you're gonna have di-sub, you're gonna have tri-sub. But for the sake here is that for our sake is that we are looking at mono substitution. So it's important that you include limited because I think quite a lot of people miss out sometimes. Alright. So let's pretend that it's gonna be substituted to um, the second carbon here, right? The second carbon here. So um, so about the naming of the compound, we must remember to put the number here by the IUPAC naming system. Now, why must we put the number? Because if we were to simply just say chloropropane, you could have 1 chloropropane or you can have 2 chloropropane. 1 chloropropane would be if the chlorine atom was substituted on the first carbon. Yeah. So we must be clear to say that it's on the second carbon, so it's still chloropropane. Now it doesn't matter where I number my compound from. In this case, because if I were to start from the left, first carbon, second carbon, third carbon, my chlorine atom will still end up on my second carbon. So it's the and if I were to start from the right, it's still also the second carbon. So therefore, it's 2 chloropropane. But what if we were gonna have like pentane, but then we have our chlorine atom substituted here. Now here's the tricky part. So if we want to start numbering from the left, we'll find that chlorine is attached to my fourth carbon. But if we were to start from the right, then chlorine is attached to my second carbon. Now in this case, what we always want to do is that we want to give the lowest number possible. Therefore, in this case, since if we start counting from the right, it gives us the lowest number 2 as compared to 4, then we will name it 2-chloropentane. So this is how we name the compound, yeah. So it's just a good thing to take note of. And whenever you write a name, make sure that whenever you're separating a number from letters, you always put the hyphen. Yep. But whenever you have, for example, you have a pentane and then you have di-substitution, like 2 chlorine atoms found here. Now in this case, we'll name it 2,4-dichloropentane. Now the thing about this is that it doesn't matter where I start numbering because 1, 2, 3, 4, 5, from the left, or 1, 2, 3, 4, 5 from the right, I'm still gonna have my chlorine atoms on the 4th carbon, on the 2nd carbon, either way, right? So it doesn't matter where I name here. But if you recall earlier, if we have our chlorine atom on the 3rd carbon here instead, so if we name from the left, so 1, 2, 3, 4, 5 below, we'll find out that our 2 chlorine atom will be attached to carbon 2 and 3 respectively. But if we want to start numbering from the right, you see that our chlorine atoms are attached on the 4th and 3rd carbon respectively. Now, because we want to always look at the lowest number that we can ever name it, so we're gonna follow from the left this time round, and we're gonna name it 2,3 dichloropentane. Now, remember that I said a hyphen for when we try and separate a number from a word letter, but when we try to separate the 2 numbers, we're going to use a comma. So that is some important rules of the IUPAC naming system that you must take note of. Alright? Okay, so now we're going to look at this free radical substitution. So this entire process is called free radical substitution. For your sake in the exam, please do not use the shortcut, the short form, sorry. Always write it out in full, the entire name. But for our purpose, we just use it as FRS. Now it's very simple. There are just 3 steps to this entire reaction. So we have IPT. So these are the 2 things. Give me a moment. Yep, okay. Just trying to make sure the microphone's on. So IPT, so we have initiation, propagation, and termination. So there are 3 steps to this reaction. So just remember that a good rule of thumb is that for each step, like the number, like step 1, step 2, step 3, they're going to be the corresponding number of reactions as well. So step 1 I have 1 reaction, step 2 I have 2 reactions, step 3 I have 3 reactions. Okay, so let's try to understand why we have the numbers as such. So the first thing, initiations. The thing about FRS is that I need to create radicals, and I think it's the only mechanism that we learned so far that covers like radicals, so it's very, very unique. So first thing I must do is that I must create a radical with my halogen radical. So the thing I do is that I will break the bond between the 2 halogen atoms. So over here we use a thing called homolytic fission. So if you can see here where I'm circling right now, so homo means equal. We will learn later it's called there's another breakage of bond, and it's called heterolytic fission. So we'll cover that later. But homo means equal. So that means in my bond pair of electrons, I have 2 electrons actually. So when I want to break it equally, meaning 1 electron of my bond pair electron will be going over to one of the halogen atom, and the other bond pair electron of the bond pair electron will be going over to the other chlorine atom here. So as such, whenever you're representing 1 electron movement, always use a half arrow. So this is a half arrow. If you were to represent like a movement of a pair of electrons, it will be a full arrow. So please take note of that. Okay. So over here will be create for 1 mole of a halogen molecule that we're doing homolytic fission on. We will have 2 moles of our halogen radicals. Now when we look at propagation, so over here, the first thing that happens is that we can just always see that we created our chlorine radical here. So our chlorine radical will then go ahead and react with a alkane. So the alkane that we use here is called propane. So therefore, we're going to create an alkane radical, and as well as our hydrogen chloride. So always remember that each reaction, like the product of each reaction, will create a radical. So it's alternating between the halogen radical and the alkene radical. So if my if my reagent is an alkene radical, like as we see in the next step over here, then our product will be a halogen radical. So it's always alternating. It's a good rule of thumb to remember. Now for the second step of the second reaction of the second step of the mechanism, we're going to react the alkane radical with a halogen molecule. Then for this you do not really need to show the movement of the lone electrons and stuff unless the question asks you to. But in which respect, you should always know that it's always a homolytic fission that we are talking about here. There's no heterolytic fission. So I think if I were to show the movement of electrons, it would be this, and it would be this. Yeah. Okay. So the thing about showing the arrows is that, so over here, if you look over here, is that it's a homolytic fission. So of course, my arrow should be pointing from the bond because that's where the electrons came from, all the way to the chlorine atoms over here, which is the receiving atom. Then as for the formation of our Rx over here, we're gonna need to form a bond between this carbon atom that has the radical. There's a lone electron with the chlorine atom as well. So what we don't do here is do this, then do this, you know. It's not how it works. So we just straight away pull the half arrow all the way to like a random space. So it was just over here that I just drew. So just and then have the other lone electron of from the alkane radical to be directing towards here too. So yeah, that's how we form a bond, because a bond requires 2 electrons minimally. I mean just 2 electrons. Yeah. So there we have it, and then you can see here the chlorine radical that's formed. It goes and react with our propane, and the reaction goes on and on. Termination is when I stop producing my radicals. So as you can do a contrast here, my reactions in step 2, which is propagation, will always produce a radical, but termination occurs when I don't produce any more radicals. In fact, my radicals react with each other. So there are 3 possible scenarios as to how termination occurs. So first being the chlorine radical, and the chlorine radical reacts to form a chlorine molecule. Second one would be the chlorine radical reacts with my alkene radical to form my Rx, which is the product I'm looking for. And or I can have my 2 alkane radicals reacting with each other to form a this odd looking compound over here. Right, so this is just a skeletal structure that I used to represent for simplicity's sake. Yep, so that's the bond that formed in between the 2 compounds. And yeah, and there you have it. That's our free radical substitution. Okay, right. So next one, I'm going to do a reaction here. I'm going to form an alkene from an Rx. Now, an interesting fact is that there is no direct way to form an alkene from an alkane that we have learned of so far, even though I think there might be some online, like some other reactions, but that's not in our syllabus. So the only way that we know of in our syllabus is to form an Rx first, then after that we move the HX to form our alkene. Okay, so how do we form an alkene from an Rx? So over here we're going to remove 2 atoms that are located adjacent to each other. So the rule of thumb for elimination reactions is that I must make sure that the things that I'm trying to remove is that they are located adjacent to each other. So I cannot remove like for example, I cannot remove this, right? Because it's not adjacent to each other. So we must always know that they are adjacent to each other, and they are bonded to the carbon, right? So bonded carbon, and they are adjacent to each other. So that's a quick rule of thumb. Oops. Yeah. Okay, so now the reagents condition I'm going to be using here is ethanolic NaOH and heat. Yep, I will cover a bit more about the why we use the alcoholic medium rather than aqueous later on. Yep, as we touch more about the bases and acids, acid and bases. So so from Rx to an alkene, we're going to use ethanolic NaOH and heat, right? Then it's going to be forming propene. Then if you want to reverse the reaction by adding HX to the CC double bond, we're going to be reacting it with group 17 hydride. So it will be HCl in this case. We just know that whenever you're trying to add HX, it's always in a gaseous state, right? Okay, even though we cannot form an alkene directly from an alkane, but we can actually form an alkane directly from an alkene. So what we do here is that we use hydrogen gas, nickel catalyst with heat. Alternatively, we can use hydrogen gas and platinum catalyst. So you always need heat when you use nickel catalyst, but you don't need heat when you use platinum catalyst. So just choose either one will do. Yeah, but I know more commonly they will put this, but I don't think it really matters. Okay, so now that we created our alkene, let's go on to find out what other reactions are there. Yep, so I'll be illustrating the next mechanism as when I show an example about how we react. So there are actually multiple reactions that an alkene can undergo. So let me just write it down. Okay, so the next reaction that we were trying to look at here is that what if we want to add two halogen atoms adjacent to each other to the CC double bond. So what we're gonna do here is we're going to use bromine for example. So what we can do here is that there are two solvent that we can there's a solvent that we can dissolve in, which is in an organic solvent. For example, the most commonly used is CCl4. If not, we can just use the halogen molecule itself in its standard state. Okay, in its standard state. So for bromine, it'll be liquid. Okay, so I'm going to illustrate the next mechanism. It's called electrophilic substitution. Okay, so similarly, there are also 3 steps to this, as you will find with a lot of mechanisms that we learn 3 steps. Actually, it depends, but most of it's 3 steps. Okay, but anyway, so my first step is that I think this is 2 steps, sorry. Okay, but anyways, so I'm gonna have my propene here. Okay, so I'm just, oops. Okay, I'm not gonna draw the H atoms of in this example, but you should always draw it out, yeah. Okay, so the first step is my attack, electrophilic attack. So recall that this CC double bond is very rich in electrons, so therefore my electrons also be from here. So that means my bond pair of electrons will attack this bromine molecule. Okay, now we will be attacking only one of them, and now we know is this breakage of the bromine molecule bond is that it's a heterolytic fission. A heterolytic fission. Why is it heterolytic fission? Hetero means different, quote unquote different. So that means it's an unequal distribution. So that means my bond pair electron will just go towards one atom, one of the atom, which is the bromine here. So now why is it that it will go there? Because if you recall under chem bonding, we know that because of sometimes that our movement of electrons, so therefore we have sometimes slight uneven distribution of the charge, dipole charge. So sometimes we're gonna have so in this case the side of the molecule that has the delta negative charge will attract the bond pair of electrons to itself, while the side with the delta positive charge will be the one being attacked by the bond pair of electrons in the CC double bond. So always remember to include the delta positive and delta negative charge. It's very, very important. If not, you cannot really show how why the bond breaks like that. Okay. Yeah. Okay. So after this, it's gonna produce our um, oops, sorry. H no BR. Yeah. Okay, so it's gonna produce our this product here and our bromide ion. Transitive space. Okay. Now why is it like that? Now you may ask, why is it on this carbon instead of this carbon that we're gonna have um, uh, the positive charge and the bromine atom attached to this carbon. If you recall, there's a thing called Markovnikov's rule. So Markovnikov's rule, the gist of it is that it states that like yeah. Okay, so the rule states that when electrophilic addition occurs in an unsymmetrical alkene, um, the major product of the reaction involves the formation of the more stable carbocation ion as the intermediate. So that will be forming our major product. So we always want to illustrate what's the major product here. Now, because this is an unsymmetrical alkene, a symmetrical alkene will be something like this over here, or this, for instance. So those are symmetrical alkene, right? But over here, because it lies over this side, so it's a bit different, yeah. Even though you might think it's symmetrical. So over here, a good rule of thumb is that the okay, I will explain why is it that we have the positive charge on the second carbon here, because as you can see, if we were to compare these two carbons over here, this carbon here has like lesser like electron donating alcohol groups. So the main thing that we're always talking about here is electron donating alkyl groups. So in the electron donating alkyl group, it disperses the positive charge here. So actually, I'm gonna go and illustrate a difference between this situation here versus the situation here. So I'm just gonna do a bit of link back. So sometimes in questions involving alkanes, right, they're gonna probably ask you like, theoretically, what is the major product of this FRS reaction? So in the theoretical sense, I'm gonna look out for products that have the highest probability of form based on the number of hydrogen atoms that are available to be substituted to form that specific product. So if I'm going to say I'm going to form 1-chloropropane, notice that I can find that I can substitute any of these hydrogen atoms that I've highlighted in yellow to form my 1-chloropropane, because why? The chlorine is on the outermost carbon, as you can see. Yep, sort of, yeah. So I have 6 hydrogen atoms, so there's a higher chance of me forming our 1-chloropropane than if I were to say my middle 2 hydrogen atoms connected to the middle carbon. So that's why in the theoretical sense, my major product will be 1-chloropropane, while my minor product will be 2-chloropropane. So one's major, one minor. This major, this minor. So I'm going to give the ratio since there are 6 possible hydrogen atoms that can be substituted to form my major product, and there are only 2 for minor product. Let me just simplify it. Yep, so there we go, we have our ratio. But if we're going to look in reality, so this is theoretically, but if we're going to see in reality, so in reality, things are a little bit different here. Like the actual proportion may not be this, right? Okay, so why? Why is it so, like, yeah, why? So if we're going to see in reality, right, so I have 2 possible scenarios, since I'm going to form my 2 different products, that my radical, my carbon atom is the radical, there's a possibility that's on the first carbon, and there's also a possibility that's on the second carbon, and that's how we give rise to the 2 different products, right? So now the thing is that we always look for stability and most reactive. Now how do we determine what's the most stable here? Because I say more stable equal to more reactive, and this is also the thing for our Markovnikov rule. So most stable, more reactive equals to a major product. Right, so major and minor. So how does it, where does the stability idea come in here? So like if we trace back, we're always looking at this electron donating alkyl group. Okay, so if you were link it back here, if we're going to compare carbon 1 and carbon 2, you can see that over here there's a bit of difference. So there are 2 electron donating alkyl group attached to my second carbon, whereas if you're going to see for my first carbon here, there's only this one big alkyl group. So electron donating alkyl group. So another rule of thumb that you can compare is that of the 3 groups that is attached to my carbon radical, 2 of it on this second carbon is alkyl group, then only 1 of it is an alkyl group, and the other 2 being the hydrogen atoms. So you can tell here there's more difference. So what does it mean when I have more electron donating EDG alkyl group? Okay, you just say ED. Okay, but don't write ED in the exam, right? Just say EDG alkyl group. So what does it mean when I have more? So that means, remember, alkyl groups are electron donating, so that means, and also my carbon radical is not having an octet configuration, so it is electron deficient. So if I want to stabilize it, I need to make sure that it's more. Anyway, when you have an octet configuration, you're sort of like more stable, right? So just for an idea here, so it's like octet equal to more stable. So what can I do to, like, make it like so-called more octet? It's because when I have more electron donating alkyl group attached to my carbon radical, it's gonna become more stable in a sense. But in the exam, you just write because there are more electron donating alkyl groups attached, and then it reduces the electron deficiency of the radical, because it reduces the electron deficiency to a larger extent. Therefore, the product is more reactive. Since it's more reactive, that's why we have our major product. See, more stable, more reactive, major product, because electron deficiency is uh, is reduced to a greater extent, larger extent. So if we were to look over here, by the Markovnikov's rule, it's almost the same thing, but except there's a difference here, alright? If we're going to see this carbon here versus this carbon, I know I've been circling so much that you can't really see it. Okay, the thing is that this carbon here is a radical, okay? But there is no charge. There's no positive charge. This carbon here has a positive charge because why? It lost an electron. So if you can see over here the bond electrons that we have here, so there's 1, 2, 3. Okay, carbon is like there has 4 valence electrons, right? But because it lost one, therefore it acquires a positive charge. But if you were to compare here, because it says this is a homolytic fission. Homolytic meaning because if you're gonna look at the chemistry of how we're gonna form a bond, one electron, in this case, from 2 halogen atoms, one valence electron from each halogen atom is contributed towards this this bond pair of electrons here. Okay, and when I have a homolytic fission, one of my the electrons that came in here in the first place is actually donated back, so called. It goes back to the same atom again. Okay, so that's the beauty of homolytic fission. But that's why this carbon, it still has its original 4 valence electron, but it's not octet. Okay, therefore you don't say that it has a positive charge. But if you were to compare here, because it's a heterolytic fission, and if we look over here, the bond pair of electrons, so we have 1 electron from maybe carbon. Let's substitute it here. So this electron comes from here, this electron comes from the other carbon. Now because for example, by the Markovnikov's rule, right, we have this bond pair electrons, it's gonna be donated, attack this bromine atom, and by Markovnikov's rule it forms a bond with this carbon. So you can see that this for example, this red electrons, part of the bond electron that came from the first carbon, it still goes back to the same first carbon because the bond pair electrons here, while the other electron from the other carbon goes to the first carbon. So you can see that this second carbon kind of lost its electron here, so therefore it has a positive charge. So this is very different. Okay, so like I say, by Markovnikov's rule, it's almost the same idea as what we have here. Here's that when I have my positive charge more dispersed, in a sense it's called more stable, and when it's more stable it's equals to more reactive, and when it's more reactive it will give my major product. Yep, so that's why by Markovnikov's rule we just always want to form our most major product, and major product involves the formation of the most stable intermediate carbocation ion, as we have mentioned earlier by Markovnikov's rule. Okay, so this is the most stable intermediate cation, carbocation ion. Apologies. Okay, so now back to the mechanism. If we're gonna just look back here again, so now I have my bromide ion, which is this lone pair electron to donate. So my lone pair electrons on the bromide ion will attack this electron deficient this carbon here. Alright, now even though they are both this carbon here and as well as the carbon radical here, they are in a sense electron deficient, but the way it has its properties are quite different, like I explained earlier. One has a positively charged, one is just not positively charged, right? Like because of the valence electrons that it contains originally. So this is a very different concept. So make sure you understand that. And when I attack, then after that I will form my RX. Yay! So these are the two steps of electrophilic substitution, and so that's how it happens. Yep. Now always remember that the first step is slow, the second step is fast. As you will see in like quite a lot of mechanism, you'll find that the first step is slow and the second step is fast. Yeah, when it comes to the reaction and the movement of electrons. So that's a good rule of thumb, right? Whenever you're stuck, like, oh, which is slow, which is fast, just always see like, oh, the first part is the slow one, just because like one of it need to go out and attack, the other one's fast because it's just finish up the reaction. So that's a good rule of thumb to remember. So this is our electrophilic substitution. I do not know if I have enough space to write everything, but I'll try my best. Okay, so that's our electrophilic substitution, and yeah, we now know how to add our atoms. So, but we're gonna now apply our Markovnikov's rule again. So if I were to do bromine aqueous, now it's very different. What happens here is that I won't form my this product here. Oh wait, oops, sorry, I forgot to write the other bromine atom here. Oops, apologies for the error. So I won't form my dihydrosub alkane here. Instead, I only form a monosub alkane. Why is it so? So if we were to refer to the electrophilic substitution mechanism, so we have our first thing here, goes attack, BR, oops, sorry. So then we'll form our. So again, by Markovnikov's rule, we have this, right? But because in an aqueous solution, we have a majority being water molecules, so the amount of water molecules greatly outweighs the amount of bromine atoms and bromine molecules also, right? So then there's a major product here. So the major product of this reaction is also, we'll see that that our water molecules actually attacks this electron deficient carbon here. This is our major product. Then it will form something like this, if I recall correctly. Now, this mechanism itself is not really in the syllabus, but okay, somehow this won't break, and then it will give our OH and our Br. Okay, but please note that this is not how you actually draw the mechanism. Yeah, this part itself. It's just for illustration purposes, because it's not in our syllabus. Unless they will guide you if they will ask you to how to draw this. Okay, so the major product here is our water molecule attacking the electron deficient carbon, because as you can see here, we have a lone pair electron on our electronegative O of the water molecule. Major product in this reaction is the one with bromine, our halogen, and our OH. The minor product in this case will be BR, where my bromine ion attack the electron deficient carbon instead. So I can still form this, but this will be a minor product. Well, this is a major product. Okay, time to get your mind blown. Major, minor. So there are actually two layers of major, minor. So this is the first layer of major, minor. The second layer of major, minor is what we have seen here, Markovnikov's rule, right? Like I say, why the major product involves the formation of the more stable intermediate carbocation ion when I have the bromine atom dash here and the electron deficient carbon to be over here instead of over here, right? So that's why we also draw this intermediate product, because it's the major the most stable carbocation ion intermediate product. So if you were to actually consider all the possibilities of forming products here, I can also form this product here. Okay. Now, because of our example here, so that's why we don't show like if you were to consider the formation of this this carbocation ion instead, like when I have my Br here, my Br can still also attack here, so I will still form this as well. So there are actually three possible products that I can form from this reaction. I think this is the least possible. Okay, I don't know like what's the actual proportion, but here's like the three possible products that I can form, right? Yeah. So there you go. So that's how it works. Yeah. It's very very complicated. No, it just takes a bit of time and practice. So there's that. Yay. So that's how you form that. Okay. Okay. So now the next reaction that I'm gonna talk about is our formation of alcohol. So now we're gonna move into our alcohol. Yeah. I'll cover arenes later. Yeah, because it's like a whole different thing. Okay. So now I'm gonna form our alcohol. So this is yeah. So this set of reagents condition is a bit complicated, but you can kind of know if you can remember. So it's corn H2SO4, 0 degrees, followed by boiling with water. I can say steam. Yeah. Okay, wait, let me just write it much nicer here. Steam. So my M is not M. Okay. Well, anyway, the reagent condition here, there's three parts to it. So corn sulfuric acid, and then we form our 0 degrees followed by boiling with water and steam. As to why we actually need to use like that, not very sure. So you can probably check online or on stuff like that. Yeah. So yeah, I can only cover as much as I know of. Yeah. Oh right. I forgot to mention earlier. This part, right? Okay. Yeah. Actually, the real mechanism as to why, um, how we actually form the products is we always form like for example hydrogen bromide. So with our group 17 hydrides, we always form that. This is for our reaction. So because our Br minus, so it's still here, then it will attack this hydrogen atom, and then this bond pair electrons from OH will break, and then it will go to oxygen. So this thing about chemistry as to why like it so-called loses, why it has like a positive charge. So it's actually very interesting. If I just trace back a bit, sorry. Why it forms a positive charge here is because if you imagine that like your water molecule, right, then it forms carbon here, so electron deficient carbon. So this bond pair electrons attack this electron deficient carbon, right? But then the thing is that if you see how the bond electrons goes, so in a sense, like one of the bond pair electron that I donated is some kind of closer towards carbon, the carbon atom. So in a sense, this O atom kind of lost like one of its electron. So whenever you like lose an electron, you know what happens. Yeah, you have to add a positive charge to it. So this is how you would draw like the mechanism itself if they ask you to. So yeah. So as to how the OH bond breaks from water molecule to form our OH here, see, is my bond pair electron from OH bond will break, and then it's like a full arrow. It goes to this O atom, this electron deficient, as you can see here. Then my bond electrons from my bromide ions, lone pair of electrons, will attack the hydrogen atom, and then I'll form a HBr. Yep. So whenever you represent it in like an equation, we must always be very very careful. So in this case, it will be plus H2O plus Br2. Now a lot of people miss out on this water molecule, so please take note. Okay, so I'll form a Br, and I'll form an OH, and I have my C, and I will have my hydrogen bromide. So yeah, here's the thing. Okay, I'll take a short break once we are close towards finishing our alkene, and then I will go on to alcohol from the other parts onwards. Yeah. Okay, so we're gonna go back to this alcohol thing. So it's a corn sulfuric acid and 0 degrees Celsius, as well as followed by boiling with water or steam. Now, what's the other way that we can like form an alkene from an alcohol, right? Like a secondary alcohol. So over here is a secondary alcohol is 2-hydroxypropane. So because alcohol is a substituent here, so therefore let's call it 2. Oh, wait! I just realized something. I don't think it's supposed to call it like that, right? No, this is not how you're supposed to call it. Yeah. This is just realized that alcohol is like way above like the priority rule for like alkanes, so it's actually propan 2-ol. Okay, please be very very careful as like how you name it, because sometimes it can be like, oh, they say, oh, I see OH group, and say, oh, hydroxy, but it's actually propan 2-ol. Okay. Now, as to why we put a 2 is here is because it's attached to the second carbon, so that's why. Yep. So it's propan 2-ol. So it's not, if you just say propanol, it can be our OH group can be attached to the first carbon and the second carbon, or yeah, it's ambiguous, right? So that's why you say propan 2-ol. Okay. So the backward reaction for this is the reagent conditions are when we want to remove like a H and the OH, right? So that we can form this double bond. Is that okay? I'll just leave this on. So the reagents and conditions are kind of similar to this, but just that actually not so similar, but it's kind of similar. So we need excess con H2SO4 as well as 170 degrees Celsius. That's what is specified. Yeah. Now, why do we use excess con H2SO4? It's because concentrated sulfuric acid, in this case, acts as a dehydrating agent. So because it acts as a dehydrating agent, so it's so-called like, because we want to remove a water molecule, right? So we need to remove water molecule, so it's like so-called dehydrating. You know, like when you lose water, it's like you're dehydrated. So in this sense, it's called dehydrating agent. So just note that this excess here, okay, excess corn sulfuric acid must be there, and the temperature must be specified is 170 degrees Celsius. Yep, and not anything else. So please take note. Okay. Yeah. All right. So one good thing to know about this is that sometimes the question may ask you about might tell you about the industrial method. It's like, oh, I'm going to give you like some reagent condition which corresponds to the industrial method, though it's quite very rare, but it might be possible too. Okay, so I think it's good to take note of this. Like what is the reagent and condition for this? So it'll be the addition of water molecules to an CC double bond. So I'm gonna write in blue here. I'm gonna go clean this up a bit later, so that it's much more clearer. So what we're gonna do here is that the reagent's condition is H2O and H3PO4 catalyst, which is 300 degrees Celsius and 65 atmosphere. So water is actually not part of the reagents, but so this is the set of reagent conditions. So it's a H3PO4, which is our catalyst. Then we have our 300 degrees Celsius and 65 atmosphere, which is the pressure. Yep. So with that, I believe I covered most, if not all of alkene reaction. Oh wait, yep. There'll be the oxidation too, but then I will. Okay, how about we just cover it right now? Yeah. Okay, I know this is all over the place. Okay, so let's cover oxidation of alkene. So we have our favorite propene here. Yeah. So we're gonna use it as a oxidation example. So oxidation, when I say oxidation, there are actually two types of oxidation. So the first type is being the mild oxidation, not cold oxidation. The other one is strong. Now, why is it mild and strong? Firstly, we use a cold reagent. This one is a with heating. So therefore, mild and strong. Yep, because like when you have heat, it's very very powerful. So it's strong, you know. Okay, so when it comes to this alkene oxidation, it's always very important. As we learn down the road, we'll start to see this potassium dichromate as our oxidizing agent too, and also our KMNO4. Now, a very important rule of thumb is that to break my alkene bond, just think of it as like, oh, very very hard to break. You know, it's like double bond. That's why I must use a stronger oxidizing agent, so it's KMNO4 rather than this potassium dichromate. So potassium dichromate is no. Always the oxidizing agent here that we always use is KMNO4, potassium manganate. Okay, so there are actually two possible medium that we can do this. So we can do acidic medium, or we can do an alkaline medium. Now the medium as to which this occurs doesn't matter, but then we will see the different products and our observations as well. So let's say we have our propene here that we're trying to oxidize, sorry. Yeah. So when we oxidize this, okay, let's talk about mild oxidation first, yeah. So it's cold. So the reagent condition is for example, let's just use our acidic medium here. So it's just cold. Yeah, it's just cold. Yeah. Okay, so what happened here is that we talk about mild oxidation. Is that I would, instead of fully breaking the double bond, I only break the second bond, the second of the two bonds. One of the two bonds break. Instead, I will add two hydroxyl groups to the adjacent carbon of the CC double bond. So therefore, we have these two hydroxyl groups added. So therefore, we form a diol. Okay. So it's 1,2 propane diol. By the way, I think this is propane diol. Yeah. Let me just call it 1,2 propane diol. Okay, so that's our more oxidation. We always add two OH group to that. Now, when we come to our strong oxidation, or this is where things get really really interesting, because the possible products that might be formed are ketone with our CO2 gas, as well as our carboxylic acid. Now I'll show you why. Now, okay, using propene as an example here. Now, when I break this CC double bond, I'm gonna end up with it's gonna fully break. Okay, so a good rule of thumb is that whenever I break a CC double bond, the carbon attached to the double bond, I will add an oxygen atom to that. So the CH3, and then because there's to every non-alkyl group that's attached to the carbon that's previously bonded to the CC double bond, I'll add an O as well. Okay, so make sure that the bond doesn't point towards H, it's pointing towards O. Yep. Okay, remember it's only the HR, not the alkyl group itself. The H is supposed to be here. Yep, sorry. So in this case, I'll form a carboxylic acid. So this is our first product. But then because this is acidic medium, so therefore our carboxylic acid is not neutralized, so it just remains as this. Okay? So then next, my carbon dioxide. Now how and why? Where do I start from my carbon dioxide? Remember this other product? Yeah, it's gonna form because I have my this first, right? So it's gonna form my O here first. Then I have this H, this H, this H. Oops, it's only supposed to be 2, yeah. Okay, so like I said, because of the H bonded to the C that was previously bonded to a double bond, I'm going to add O to this H. So you know what's going to happen? Yep, so I'm going to have OH, OH, OH. So if you can recall, it forms our carbonic acid. But because it's, again, like in strong oxidizing mean, it undergoes strong oxidation, and it's also quite unstable. So what is that? What it gets? What happens that it further oxidized to, it's actually unstable in water. My apologies, and it dissociates into our CO2 gas and our water molecule. So you can kind of see it's like this CO2 here, and then our water molecule here. But then of course it's CO2. We know what's this. Yeah. So there's that. So that's how I form my carbon dioxide here. So what about you? You'll be asking like, oh, how about ketone? Okay, so we can't illustrate with this example because yeah, because because of this example. So what if I were to say that we were gonna form butylene? Okay, so butylene. So when I break this bond, okay, maybe that's that's not how it works. Okay, so to form a ketone is that I need to have as you will learn later. So ketone, there must be 2 alkyl groups attached to the carbon. That's how you form a ketone. So meaning so for example, if I were to use it's not really propene in this case. But in this case, I have 2 R groups. So in this case, I'll break the bond. Because it's not hydrogen atom attached to this carbon that's bonded to the CC double bond, so I cannot form a carboxylic acid, nor can I form a carbonic acid. So what I'll do is that I'll retain my alkyl group. Like I said, I don't add anything to the alkyl groups. I only add to the double bond in this case, which is the O atom. So that's how we form a ketone. Yep. So this in our acidic medium. So if I were to illustrate in our alkaline medium, it would be slightly different. So I'm just going to use blue here. So because in our in a alkaline medium, this will get neutralized. Our carboxyl will get neutralized. So what's going to happen here is that I'll get an O minus, and then I'll CH3. So that's what happens. This is our carboxylic ion. Oops, sorry. Carboxylic ion. Okay, so the next thing that occurs is that this carbonic acid. Now, because it's in the alkaline medium, so firstly it wouldn't exist as carbonic acid. Instead, it will just exist as a carbonic ion. Yeah, but it doesn't get broken down into it doesn't get dissociates into carbon dioxide. It just stays as carbonic ion, and then we have our water molecule here. So if we're now talking about ketone, it's still the same. There's no change. It's just ketone 2 in the alkaline medium. Now there's one last thing that's very quite interesting, is that if I were to break this, so for example I have like for example, oh, not this, it's not erasing. Okay, anyways, I don't care what R groups here, it's R1, it's R2. So what happens when I break these bonds is that I will add O to the H. So I'm gonna form a dicarboxylic acid. Now because it undergoes further oxidation, okay, so let's go further oxidation. It will be further oxidized and broken down to give my products. So it will form 2 CO2 and H2O. Let's see, CO2 here is CO2 here. Okay. From CO here and the H, but then because I'm going to undergo further oxidation, so CO will be further oxidized to CO2. Therefore I have my 2CO2 and my 1 molecule of water. This is the thing about dicarboxylic acid that we form here. Actually, it's just not, it's not like dicarboxylic acid. Sorry, it's ethane dioic acid. So this is the special case here, ethane dioic acid. Okay, this remember is in acidic medium. So what if I were to illustrate in alkaline medium? Sorry, I just forgot to change the color. So if it's in an alkaline medium, then what happens is that, as we recall, as in like the carbonic acid here example, is that it it doesn't like break down to give you like your carbon dioxide. Instead, it just gives you a carbonic ion. So the same thing here is that I use my 2 carbonic ion and my H2O. So that's how different it's like an alkaline medium versus acidic medium. So all this thing here. So that, I think, will give you quite a bit of clarity on like the entire process. So I'm gonna erase it later, and I'm gonna refine everything, and we're gonna cover the rest of the reactions that is being taught. So this is quite a long first part, but it explains quite a lot of stuff, and hope it really helps. Yep. So thank you. Observations that we use when we do strong oxidation and mild oxidation as well. Okay, but just take note that this one, effervescence, is only for strong oxidation. Mild oxidation, we don't have that. Yeah. Okay. So okay, so the thing is that for strong oxidation, in acidic medium, so be it strong or mild oxidation, we're going to have our purple KMnO4 decolorize. Because why? In our KMnO4, we have our Mn ion. So Mn actually is, manganese is actually has an oxidation state of +7 in KMnO4, and it's being reduced to +4 in MnO2. So therefore, since there's a reduction, the purple KMnO4 decolorizes. Right, so because it's oxidizing agent, so it will be reduced. So in a mild oxidation, we're gonna have purple KMnO4 decolorize, and as for in alkaline medium as well, we're gonna have purple KMnO4 decolorizing, and we're gonna have brown PBT of MnO2 form. So this is applicable for mild and strong oxidation, but only in strong oxidation, acidic medium, then we see there is effervescence. So the effervescence we're referring here is carbon dioxide. So if you recall, whenever I have a terminal alkene, right, so and then there's 2 hydrogen atoms attached, then it's going to form my carbonic acid, but it's unstable, so it dissociates in water to give you your carbon dioxide gas and your water molecule. So the effervescence they observe is actually carbon dioxide. Then the gas evolved, which is carbon dioxide, forms a white precipitate in calcium hydroxide, which is, in other words, lime water. So that's how you do it. If you just recall in alkaline, it's because my carbonic acid is right away neutralized, so you just form a carbonic ion and it doesn't dissociate to form carbon dioxide and water molecule. So there's no effervescence. Yeah, just take note of that.